So okay, guys, let's continue. Yeah, I got sick, so can be a little bit slower in terms of the thinking, but I'll try to do my best. Beside that, so let's just continue. Last time we spoke about all these topics, right? And we stopped on the thresholding of the images. And let's just focus on this part because it's we need to cover it before we go to the next topic. And in terms of the thresholding, basically the idea is that we take the image that we have, and then we want to identify some threshold, some value, which will separate background from foreground in our case. And the idea that there are different methods how to achieve that. Basically, we will take a look on a couple of them. And after that, so for example, if we specify the threshold, we can create a new image, which is a binary image. And for example, if the intensity of particular pixel is higher than the threshold that we identified, we will say that this is a true foreground, and otherwise it's a 0, which means background. So this is just as a formula that explains what we want to do. And let's just take a look on the following examples. So while I prepared 3 examples here, and we will take a look on some generic images that usually we can see in case if we go to the internet and check, for example, thresholding images scikit image. You can open it here, and yeah, so basically this is some generic images that usually showed to demonstrate the thresholding. So let's start from the first example. And in this case, what we do, we just like from scikit image, we want to we just want to threshold it. Yeah, so we import data, but data basically it's image of this person. So plot, yeah. So let's also import matplotlib as plt, and also we need probably import numpy as np. For now, probably it's enough. Yeah, so and we can make a plot im show camera cmap gray. And this is a picture that we want to threshold. Basically, we want to identify what is a foreground and what is a background. And first approach that we can use is just simply to get some value. For example, here we specify some manual threshold. I specified it as 120. You can take a look and check what is a like a data type and the range of values in the image. In this case, it's supposed to be the range of intensity values are from 0 to 255. And then what we do, we simply use the like a Boolean condition. So here we check whether the image, we call the image as a camera, is greater than threshold that we specified. And in case if it's greater, we will say that it's 1, otherwise it's 0. So let's just execute it. And here we get 3 images. So yeah, maybe if you work in your notebook, you can switch here from yeah, something like that. So let's just switch and delete this part. Wow. So yeah, something like that, just to make it 3 in a row. So this is the original image, and then you can see we have a histogram of values for this image, and we randomly selected a value of 120. And now everything which is like more brighter in the intensity, so basically this area, everything becomes like a true after we thresholded it. And this is a binary image. And this is a very standard approach to use it in the in the image analysis, because usually we want to understand what is the shapes and morphology of the images and not just intensity values. So, and then let's just take a look also on a couple more examples. Give me a second. So guys, can someone say something? Just want to check that everything works.
1, 2, 3.
Okay, yeah, thanks. That works. So yeah, basically this was the first example, but now let's check another generic example that usually people demonstrate. It's a page, and this one is more interesting probably, because in this case you can see that there is an uneven background on the image, and then usually those typical approaches for thresholding might fail, because if you have a gradient of values, then it's much harder to understand what is a background, what is a foreground. And right now, so we are working with the example where we assume that we have two representations. So one is a foreground, another a background, and we assume that there is some separation in terms of the distributions of the foreground and background just by intensities of the pixel values. So let's just briefly take a look on this part. We will not put it and run, but just like I just want to show you that in this case, for example, we cannot right away to see what is the foreground, background looking on the distribution. So in previous case, you can see that probably it's a 3-model distribution, and you can say that, okay, so some values among this range probably separates some class 1 from 2 and 3. Also, you can put, for example, value here, and then probably you will identify just this peak, and you will see what is positive for this one, just as a side note. And in this case, yes, so in my mind, it's more interesting because usually pictures and images are not perfect. And in this case, we see it right away that we have the shading or grade of illumination here. And yeah, basically, if we try to put one single value, you will see that part of the image is like blacked out, which is not nice. And you can try to play with that. So yeah, let's anyway just like copy paste it and let's execute it. So, and you can try to change it, this value, to another. For example, try to put 175 and see how it works. So basically you can identify and separate like a background from foreground. And in this case, probably foreground for us, it's the values which are like lower in intensity. And this is just as a kind of note. Yep. And you can try to play around, identify maybe there are some like nice value which can separate everything. And for example, in this case, if we go like to the left side of the image, let's say we specified as a value 75, you can see that we start losing some like information on the right part of the image in case of the binary image. And still there is some strange happening here. And we will later see how can we deal with such cases where there is some uneven background. We will try to use different approaches for that. But this is just like to showcase you that how it works. And the last example, it's our like a simple example of microscopy image where we have nuclei, and also here we specified, for example, threshold is a 120, and maybe here we can try to put the value between like 50 and 100 and check how it will look like in the end. So let's see. So for example, I put it as a 75, and image is we need to, yeah, so for that we need to execute this part. So let's just import this part. And also we need to read an image. Okay. So yeah, in case if it's a 75, then maybe it's a better value than it was in the example. So here, for example, we had 120, right? And then some parts are not so nice as it here. But still we have something on a background, and later we will try to deal with such things a little bit later. Okay, so this was a like very hard-coded approach. You, for example, can manually inspect the histogram first in your cases, and then you can say, okay, I want like to use as a value just some manual specified. So if be honest, it's a valid approach, you can use it, but usually we prefer to optimize and to use some approaches which can right away provide us the potential value. And so the one approach which is like very popular in terms of the binary thresholding, it's called Otsu thresholding method, and you can check probably the Wikipedia. Yeah, so you can go and check the Otsu method, and basically there is an explanation how it works. The idea is that usually we assume that there are B-model distributions, so that we have like two distributions, and then it tries to optimize the variance of the this like distribution, so like the variance difference between distribution. So you can see that it's like builds the curve, and then we just identify where is the maximum, and it's gonna be as a potential thresholding for your case. And the assumption, yes, so for the method that usually we think that there is one value which can split two distributions. And let's just take a look how it works for the cameraman example. So we can execute it, and now so you can check that we specified threshold not like manually, but by using the method, which is like from scikit image filters. It's a threshold Otsu, and then we just like use the mask to be set as a condition of camera is greater than threshold. So yeah, and for example, in this particular case, you can check that the value was something around 100. And yeah, so but you can ask, for example, okay, I see that there are probably 3 distributions, not 1 or maybe even 4. How can you deal with such cases? And there are some approaches that you can utilize. For example, there is a method which is called multi-otsu, and then you can specify how many classes you expect to have in the image. For example, for this particular one, you can say that, okay, I expect to have 3 distributions, and then it should work. So yeah, this is a generic example too, and as you can see, so it doesn't like solve the problem. So we still have incorrect mask or like in the poor mask, because some parts are like well defined, but this area like totally black, which is not a correct solution for this particular task. Because if you look by eye, right, by eyes, we see that there is a like a distinguishable foreground and background. And now also for the microscopy image, so this is where it made the threshold, so it's like around 100, and this is how it looks like. So okay, but now in case if you have non-even background and you want to deal with that, you can use local adaptive thresholding. So let's just take a look on it. And probably we will skip this part. So this is how it works in case of the cameraman example. As you can see, it's like probably detects edges nicely, but it's not really separates background from foreground in this case. So, and probably it's better to have in mind that you usually need to know which method to use in which case, in which cases, right? But let's take a look on the this approach when we use it with the page example. So page is like just a example from the data module out of scikit image, and you can see that it's like nicely working and identifies the text and the background. So let's just copy paste it and examine it. So yeah, basically for that you need to specify the function, which is a threshold local, and then yeah, so there are some arguments that you need to provide. So block size is basically what is the context we want like to use for particular area of the image. So for example, if you focused in some area, you can specify how large is the view that you want to take as a like to measure the threshold. And in this case, you can see that we got the threshold again, but it's not a single value. And this is a different values for different parts of the image. And because of that, we cannot like right away to use it in the histogram. So for example, if I do th, you can see, so basically it's probably the same size shape of the array that we have thresholds for each particular pixel. And this is how it works. And then also you can check how it works with microscopy image. And in my mind, so what I see that probably this method can identify some edges in this case. So we do thresholding and then it can identify some variation, but still not something that we expect to have. But now let's try to solve some tasks together. So basically you saw that we used local threshold local method, but now let's spend some time, and your task is to implement a thresholding by not using the threshold local, but let's use approach that we used before. So it's like a correction of a background. So let's correct background, and we will work with this particular example of the so our image, it's a page. You can load it by using the following syntax. So where it is? Yeah, so from scikit image, you need to import data, and then page is data dot page. So and you can use it in your code. So and our task is to perform the uneven background correction, and after that to use simple Otsu threshold, not a local one, but one Otsu threshold, get particular value and represent the result. So you have 10 minutes to accomplish this task. And if you have any questions, please ask me about task. And then we will switch to another one. It's basically to do something similar, but in this case, we will try to split the image in some patches and identify thresholds per patch and check whether it works or no. So guys, any progress? Any ideas how to start? Okay. So Dastan, can you share your screen and describe what you did? Let's do it. I will stop sharing my screen.
I will try to just send my code to the chat. I think it will be easier for everybody.
Okay.
So this is the initial formula which was provided on the page on the GitHub, and after that I applied binary to separate background from image, and I didn't have time to find some smart way to estimate the threshold, so I just rendered it multiple times, and threshold 0.7 was looking the best.
I see. But so Dastan, we want to do it slightly different. So here you do it as a background and you used threshold local, right? But we don't want to use threshold local. So basically the idea is that we want to approximate or like background, and we want to do in the same way as that we did before. So for example here when we did it, we used like a blur, right? We blurred a lot the image. So for example, when we did it here, so we want to use something similar here. So we want like to assess the background by the blur, and then instead of, so in this case, let me just, yeah, so basically probably I will put it one more time. So we want like to have our image, it's an input. So input image is a page from scikit image. Now we want to measure the background using, for example, a Gaussian filter. Yeah, in the same way, and then perform background correction. And after we get the corrected image, use Otsu for corrected image and get the result and get the final mask. So something like that. Okay, let's check. So we have two solutions. Okay. So let's check both, right? Okay. So this is a first one by Dastan. So the idea is that, yeah, we use Gaussian for background. Then we do image float pages type and p float 64, background float. Okay. Then corrected image float divided by background float, also threshold. Okay. And this is the result. So looks decent. Yeah, so when you can see here we adjusted the background, and then the variation is not so large as it was before. Yeah, and now let's check also Anna sent her solution. So, and in this case we get yeah, but this is for camera. Let's add it as a page. So page is data page, and then we here want to have page. Yeah, and let's just also print the result. So let's do it in this way. So we want to have figure axis, and we want to have 3 images, right? And we want to put axis 0 in show. It's a page cmap gray. Here we want to put, let's just put background. Let's see how it works. And then the mask. Oops, my bad. So yeah, this is the result. Looks decent to me. So basically this is a first image, the input. Then this is how the background looks after we measured the background using the just like a high sigma, right? And then we divide page by background, and then we take a look on the result. So okay, you can play around with different sigmas just to see how it looks like, but yeah, basically the idea is this one. So yeah, cool guys. Yeah, this very nice. And now let's just do the following one. So now let's try to solve the task, and this one maybe it could be a little bit trickier. So the idea is that we will do it like locally somewhat, and the idea is that we want to divide the image into smaller tiles and apply thresholding to each tile separately, and then just merge the thresholded tiles into a single binary image. So let me just put it here. So the idea is that we have input image is a page again from scikit image data, and then we want to apply Otsu for parts of the image, tiles, or like something like that, and get the final mask. So let's try, guys, and you have again, let's spend like 7 minutes and let's try to solve the task. And any solution that you get, please just share it.
We shouldn't import anything from Schemage, or just shouldn't import local threshold.
So you can import from the, for example, from the filters or morphology, I don't remember, filters probably. You can use threshold Otsu, yeah, and you can use whatever you want for splitting the image into parts. If you know something, you can use anything, just like to split the image, or you can just write some for loop, and you can go through parts of the image and apply thresholding there. Yeah, probably in this particular case, you need to be kind of accurate about what are the pieces that you want to use as parts of the image. So in Anna, it's Anna Chesnakova, right? Send the solution.
Yes.
Yeah, cool, great.
And also I have a question, which like tile size we should use.
So it's up to you. You can use whatever you want. So basically, you can try to think about it. You can look on the image and then you can think about it. Okay, what should be my tile size be? And just try to do it in the way that you got like some reasonable mask in the end. So there is no like some restrictions about anything in this way. Yeah, okay, guys. And if you have any questions, then just please ask. So I don't know. I want like to get some idea. Let's just like pause for a second, guys. Or if you're like super like in the flow, you can continue and working on the task. So please, I'm like really begging you, in case if you don't know what is happening at all, and you're like, shoot, I don't understand. Let me know, because I don't know. I just want to help you, you know, I just want to explain something and that we all are on the same page.
Can you clarify what parts of the image exactly, like what does it mean apply also for parts of the image, parentheses, tiles?
Yeah, so basically, let's take a look on our input image. So this is the input image, right? And you can see that there is some gradient by the uneven background. So there is uneven background, and basically the idea is that you can split the image in parts that you like. So for example, let's say that you split it into 5 parts by vertical lines, just like as an example, and then you can.
Can you repeat? You lagged for like a minute.
Yeah. So basically, from the beginning, we have the input image here, right? And we see that there is an uneven background. But let's try to deal with that by assuming that we applying the threshold not for the global image, but just for the parts of it. So for example, let's say that this is the first part, and we can try to find threshold there, apply it, and see whether it will improve. So for example, I can split the image into 4 sub-images. It can be still the same kind of object in memory, and you can just create a new one where you will store the mask. And the idea is that you just like take this part, you apply the same Otsu threshold and treat it as a one global image, identify threshold, and see whether it helps or not, something like that. And do it for all parts that you defined. So yeah, I maybe can even create a PowerPoint fast representation. So let's say that this is our image. And there is an uneven background, so let's even try to mimic. I mean, like while you're working, I'm just playing with PowerPoint. So we have a gradient fill. Let's say that it's let's say that it's green from left to right. Yeah, something like that. And let's remove this part. Yeah, so this is our green 1, green 2. Yeah, so there is uneven background, and let's just try to, for example, work with this image by parts. So for example, you can split the image in this way, or any way that you like. Yeah. So, and then you can, and you can apply threshold for each tile and identify what is the background, what is the foreground in this case. Yeah, and the idea is that maybe if your tiling is good enough, you can, for example, avoid the uneven background, but at the same time to identify the information, like interesting information on the image. Guys, and why, while you're working, so do you have any ideas why this can be important for us?
I'm not sure why exactly do we need the tiles. Can we just apply normalization to the whole background? I don't really understand.
I mean, we already did it. So basically the first approach that we tried, it's like we normalize the image by measuring the background. So we measure the background, and then we, so for example here, it's like more clean. So here we measure the background by using the Gaussian filter, and then we subtract the background. Yeah, so we did it, and it works like very well. So yeah, so we got the decent result. We can see that there is a text, and we can read it on the whole page as a binary image. But now we just like trying to practice with working with images by splitting it into smaller parts and applying some methods to smaller parts.
Okay.
Yeah, so and why it might be useful, because sometimes you can have like a very large image, and the method that you have that works well, for example, for a smaller image cannot be applied for the large one. And you're like, okay, probably I can try to split it. And here we just practice in the way that we want to be able to split image in some way and work with that. Guys, any success?
It is a bit problematic to divide this image because its shape is 191 by 384, and 191 is a prime number, so it cannot be divided into equal squares.
Yeah, but you can be, you can try to be not so perfect in this case. You can like divide it just like by some like probably approximately even numbers, but it's not like required. So guys, okay, let's then just have it as a homework. Please work on it and just try to deal with the image in the way where you okay, we got something. So there is some page. So Nikita, can you explain what does it mean? So in pipette, is like to add some padding, right?
Yes, that's for vanilla. So when the dimension is not divisible by the length, like the size of our tile, we can just add with zeros to get some more workable shape.
Okay. Okay, sounds good. So, and also we got, oh yeah, guys, we got a lot of solutions. Nice. Nice. So let's do it this way. So Anna, can you like go over and explain and show us the result? So
Okay, just a minute.
okay. So Dastan, in your case, does it work? The final image looks decent.
It looks kind of lame, but I guess it's expected for such simple algorithm.
I
It
see.
has some noise, but overall it sort of works.
Okay, sounds good. So I can stop sharing. Yeah.
Can you see?
Yep, I can.
So I choose title size 10, for example, and I prepared mask with zeros, and then I divided by column and row by title, and for each title I calculate threshold Otsu and choose like do a matrix as binary with this threshold, and but it's kind it looked like kind a bit bad, but if we do threshold size higher, it it not works for me. I don't understand what's the problem, but I didn't see any other solutions.
That looks good. So that looks good. I like it. So basically, yeah, we can see in case if it's like a very small tile, right? Let's just think about it in a little bit. So for example, if it's a very small tile, then in right upper side there is just like nothing is like happening there, right? There is like no variation in this particular tile, but still we are trying to apply also thresholding. It finds some value and then we threshold, and because of that we got this mask as a result. So let's just keep it as a homework, and I just want to give you maybe some kind of idea behind that, so I can probably start sharing my screen again. And yeah, so the idea that you can try, for example, in this particular case, don't split it like by horizontal lines, because we see that the background, moreover, same in case if we look by this way. I mean, like that in case if we split, for example, from 0 to 50, we will have issue with the background. But you can try to split it, for example, by, let's say by 50, like step 50 for width axis, and then try to apply it there. So, and yeah, please try to play with that, and you can get some reasonable result. Maybe not ideal, but still. And it's just like to practice and play with that. But now let's switch back and let's go to the morphological operations, which is the next step after we did the thresholding. So, what does it mean, morphological operations? We will see today that we can have the binary image, and then the idea that we can, for example, try to get rid of some small objects on the image, or for example, we can fill holes, we can like expand the object or like shrink it. And there are different operations that we can use. And before we start, we need to cover one key idea in the morphological operations, which is the structuring elements. And it can be any small like array, and it will specify how the morphological operation works. So we will just briefly look on two particular examples. So this is just ones, like 3 by 3, and we have just as a small structuring element this ones, and then you can, for example, have as a cross, or you can have like as a circle. And the idea is that we will use these structuring elements to identify whether we need like to expand the borders of the shape that we have, or we need to, for example, shrink it. And for that, there are three possible things which can happen. So let me open it in a new window and we will take a look. So basically, this is a structuring element that we have. In our case, it's like a ones of 3 by 3. And for example, we want to identify whether this pattern match the image that we have. So it can fit, or it can hit, or also it can misses the object. So, and when we say that it fits, basically the whole object should be covered by the original object that we are interested in. So in this case, this is our object of interest in blue. And now, for example, we put the structuring elements inside of the image and it perfectly fits. So this is just like a definitions, and then we will see how it like plays the role on practice. So then also there could be a possibility that we have hits. In this case, you can see so that the part of the structuring element is outside of the blue object, but some part is like kind of inside of it. That is expressed by the word hit. And also it can be completely outside of the object, and then we call it like a miss, no pixel in the structuring element, cover the pixels of the object. And now, so we can perform different type of morphological operations, and the first one is called erosion. So basically we will shrink the object that we have. And this is an abstract example that we have. We, in this case, start from the numerical Python array. So you can see that it's like zeros, and then there is a ones inside of it. And as a structuring element, we have NP1s, the same that we saw before. And now we can perform erosion. And this is how it looks like before and after. So you can see that we can apply our structuring element with like a binary image that we defined. And then we will shrink it, or for example, we can use dilation and dilute the object. And in this case, how it's done, basically you need to put the structuring element to match it with each pixel, and then if it fits, then you keep the value that you had before. And in this case, you have only one fit for the image. So when we put the structuring element inside of this 3 by 3 ones, in this case it fits, and that means that we will keep only this particular element. And otherwise, if you put the structuring element outside anywhere, you always have not a perfect fit. And if it's not a perfect fit, that means that we need to kind of substitute this value by 0 because it was 1. And so yeah, let's just also like firstly look on the dilation. This is a similar idea. So we have our original image, which is for example something like that before dilation, and then now the idea is that if we put the structuring element anywhere on the image, and if it hits, then we will substitute the pixel value with ones. And this is just like a summary. So in this case, let's think about it as we have a footprint as a cross, and first we do erosion. And you can see that the blue ones are just those values where we can fully fit the structuring element. So in case if you put structuring element here, you'll see that it's perfectly fits, and this will remain in the image. But this value will not be, because you cannot put the structuring element inside of this pixel and be at the same time fully inside of the object. So this is the idea of erosion, and then there is a dilation. And in this case, if you have hit, then you need to substitute it with 1. So guys, is it clear, this part? Right? Okay, so yeah, and then we can use this operation. So let's just take a look. So this is a before erosion, after erosion. And you can see that we can, for example, shrink the objects. And sometimes, let's say that we perform cell segmentation, and we identified some like or even before cell segmentation, we have like some potential mask that will be used for segmentation. we can identify some binary objects in the image which are like very small, and usually you can try to kind of wash them away by using the erosion. Yeah, and this is an example with the simple shape. Let's say that we have a circle in the beginning, and then we have like as a structuring element like just 9 by 9 ones. Yeah, here I probably need to update the code. Yeah. No, everything is fine. So yeah, disk, it's like basically our shape in the beginning. And DE, it's like a eroded image that we will get in the end. And let's say that we want like to repeat erosion 10 times. And as you can see, so original image that we had was shrinked. We got it smaller. But in this particular case, you can notice that the shape is also changed, right? And it's not like perfect. And this is a thing that you need to keep in mind. So because we had structuring element as once, and because of that, if we apply it multiple times, it can distort the original shape that we had. And in this particular case, you can try to switch from the ones to some smaller disk that you would use for erosion. And the idea is that we can shrink some objects, and in case if it was something like very small, it will go away and you will not have it in the image. Yeah, and so for dilation, it's opposite. You can expand the image. In this case, we had like a something like as a bar, and then we expanded it by using the NP1's footprint. So, and then there are two type of methods which are called opening and closing, and they are simply a mix of the erosion and dilation in the images. So here it is. For example, in case if we have opening, we will perform erosion first, and then we will use dilation. And in this case, if we had like some large object enough, it will remain on the final output. But if it was something small, we will just delete it. So, and the idea is that you can like preserve something interesting, but at the same time to remove something non-relevant for you. Yeah, always you need to keep in mind that some small particles on the image can represent some meaningful information, so you need to kind of make the decision yourself. And the closing, it's the opposite one. So you do dilation first and then erosion. Yeah. And then there are some methods which we will cover a little bit later for filling holes and removing small objects. But now let's try to play with these methods, and we will do it with our image of nuclei. So let's do it together, and we will try to get something reasonable here. So basically, let's start and let's check. So we have our image, I hope, loaded. So yeah, this is our image. And now we want like to proceed and apply all these morphological operations to get somewhat reasonable mask for our cells. So let's do it. First thing that we can do, we can try to use a filter, like a Gaussian filter for the image. Let's just like have a little bit smoother image. I will call it like image smooth, which is a Gaussian of image, and let's say that sigma is 3. And let's plot him show image smooth with CMap gray, just like to take a look how it looks like. So, and this is our image. We just like made it a little bit smooth. We added like some blur, and now we will apply threshold. So let's identify threshold by using threshold Otsu for the image. Yeah, so image smooth, and then we will get a mask. So mask is simply image is greater than threshold. Image smooth is greater than th. So, and let's just plot him show our mask. So mask and CMap gray again. So, and this is how it looks like. And now let's try to deal with the small parts. So let's remove all of this. So this one, this one, and also we want to fill this part. So guys, and try to, so this is a code that I made. And basically the idea is to now apply this morphological operation. So please take a look on the website. You can see that they are like located in the from scikit image morphology import, and they are called opening, closing, or also you can import erosion, dilation. And let's try to use some combination of them to get rid of, for example, at least these three parts, like 1, 2, 3. And at the same time, we want like to fill this small gap here. So let's try to solve it. So this is a code, and let's try to just play around with opening, closing, and get a little bit better mask of our image. So yeah, guys, and as a kind of off topic, not off topic, but just like as a some hint, or maybe note. Let's say that this is like some note. Basically, right now we already can say that we resolved some particular task of segmentation because we got some result. It's not ideal, but some type of the result. And this is the segmentation of the cells. In this particular case, we don't have a segmentation to be to represent particular cell. In this case, we have like as a binary mask for all cells. But even in this case, it's called like as a semantic segmentation when you need on the image to identify objects of particular type. And in our case, we identified everything that we assume is a cell or like nuclei. In this case, maybe better to say that it's a nuclei. Yeah. And yeah, so you can think about it that we resolved the segmentation task and exactly saying it's a semantic segmentation. And now we just want to improve it a little bit. But later we will see how we can identify individual objects from this particular example. Yeah, so as you can see here, for example, all these cells, they are merged in one big object because we have these like bridges between them. For example, here probably we can use erosion and like to separate this one from these parts of the cells. Maybe if we go even deeper, we can probably separate this one from others, but still this one will be covered later. So let's try just like to play around. If we don't know which order to use, let's just like try to use, for example, closing first and see how it looks like. So this is our mask, right? Original. And we want to close the image. I will call it like closed, closing. And now we need to provide the image. In our case, it's a mask and then a footprint. So in footprint, let's use just a disk. And let's say a disk of size 3. We will just take a look how it works. And for the disk, we need to import it from scikit image, morphology, import disk. Yeah, disk is basically, you can create a circle using the disk function, like a binary circle. Figure axis, let's do it plot, subplots, 1, 2. Figure size is 8, 4, let's say something like that. And now I just want to plot before after. So we got something. Okay, nice, we got something. And here what is done is like smoothing, thresholded, disk, opened, and then closing. Okay, so this way around or this one. Okay, nice. But let's just briefly take a look here. Just how can we work with that? We don't know in advance how large should be expansion and like shrinking. So let's just play around and visualize it. So axis 0, it's im show mask. And now we want like to say axis 0 set title it's before, and probably axis 0, axis is off. And for the 1, so let's do it. Yeah, probably I did not execute this part right. And we want to put closed here. So yeah, and this is how it works. Maybe we need to put CMap as gray, right? And let's just take a look. So this is before, after, and for example, this part was closed. Nice, right? And now let's just try to use opening. Now we want like to open the image, and now we can say opened. Yeah, opened is opening of the closed, and then footprint again. Let's use disk, I don't know, 5. And let's just copy paste this part. So this is we want to have closed and then opened. I think that's it. So yeah, let's run it. And you can see, so we got rid of some small parts. Cool, right? Some like simple operations, and we already improved our representation. So now, for example, just like as a spoiler, we can import from scikit image morphology import label, and let's just create a labeled image, just like to get some brief idea about what's gonna happen in the next lessons. So we will import label, and then also from scikit image color, let's import label to RGB. And now let's just print our result again. So this is a lab image, is a label of our opened image. So here we want like to put opened, because it's like as a sequence, we do it like step by step. And here we want like to put label to RGB of our labeled image. And we don't need to put CMap gray anymore here. So let's just run it and let's check. So yeah, and this is what is called labeled image. Basically, for each separate object on the image, we assigned a label. Usually it's like a number from 1 to how many separate elements we have on the image. And as you can see, so right now it's not ideal. All of these like cells, they assign to one particular object, and we'll just try to improve it. But even in this case, we got some representation of separate elements on the image, which is nice. Yeah. So guys, that's it for today. Probably I will share with you some. Yeah, nice. Yeah, right. So yeah, we will cover also like a little bit like how we can fill holes and how can we remove small objects. It's somewhat similar to erosion dilation, but the idea is that we don't like fixed by this like structuring element, and it can be more flexible in some particular case scenarios. But that's it for today. Next time we will cover some classical approaches to segment cells. And basically the idea is like we want like to improve this particular representation. And then even right after that, we can start working on the homework. Not homework, but the final assignment. Which is perfect, right? Okay, guys, any questions about today's lecture? Or anything? No? Okay, then I stop sharing, and that's it.